the kind of things we've been focusing on in the last few lectures are kind of like, imagine you have a graph where the number of edges is bigger than the extremal number. And, we've been trying to find lots of copies of the graph H, where copies has kind of, the meaning of the word copies has kind of changed over time. So, right, when we were doing triangles, I was just counting triangles. With even cycles, we were counting homomorphisms. But in some sense, it's all very, different ways of measuring copies. And these bounds that we got for these specific cases, like triangles and even cycles, it's like a very precise bound. And we were even able to observe that it's tight, like at least in a lot of different cases. So the triangle, we were only able to prove it's tight in some isolated edge densities, but these ones are tight for all edge density asymptotically. So now today we're going to look at the more general question. So we have any graph H. So H could be, think of H being, if you like the Peterson graph, I guess a lot of people do. I don't really know why people like the Peterson graph so much. I think it's interesting for certain problems, I guess. I don't know. But to me, I may be a contrarian. I'm not that big into the Peterson graph. But anyway, think of H being the Peterson graph if you like the Peterson graph. Yeah, it's a counterexample for a lot of things. I just can't name any of those things. But okay, so take H to be, it's a snark. And snarks, there's some interesting, the whole theory kind of about snarks. There actually is a whole class of graphs called snarks, and Peterson graph is one of them. I guess it's like cubic graphs which aren't 3-edge colorable. Maybe it's something different than that. Okay, so right. So we want to say, okay, I've got any graph H. We don't know what the extremal number of H is exactly, but we have a good idea. Like it's equal to some particular, chi of H minus 2 over chi of H minus 1 times n choose 2, basically. And we take a number of edges bigger than that, and we want to say that G has a lot of copies of H. Now, it's really annoying to talk about copies in some sense, because again, I have to say what I mean by a copy. Today, so previously we've been looking at homomorphisms and stuff. Today, a copy is going to be simpler. It's going to be just like a copy of H and G. I'm going to just define to be a set of vertices S, which has size V of H, size, number of, so if H is the Peterson graph, then it has size 10. Basically such that there exists a copy of H on those S vertices, or sorry, those V of H vertices. So I've written it as like there's some sort of bijection which preserves edges. In other words, it's just that like there's a copy, like the set S, or maybe I can say the subgraph of G induced by S contains H as a subgraph. So like I'm counting, sets that have copies of H in them, even though, okay, I'm defining a copy to be the set itself. But anyway, is it clear what I'm talking about? So this is nothing here is going to be very precise because we're doing things in such generality. So constant factors aren't going to matter. So I'm just going to count copies to be sets of vertices that contain H. So in this kind of definition of copy, when I look at K4, I just think of it as containing one copy of a 4-cycle, not like 3 copies or the number of homomorphisms or anything like that. Is that clear? So we want to say if the number of edges is bigger than the extremal number, I've got a lot of copies of H, where a copy is just a set of vertices that contains H. Right. So, okay, just a quick thing for the audience just to see if we understand this notion of copy. So suppose I take any graph H and I ask how many copies of H are there in Kn, where Kn is the complete graph, under the definition we just gave. So any thoughts on that? Okay. So that's, I think we're getting, yeah. So I think the n over v of H would be if you wanted disjoint copies of H, then that's, yeah. But this is the thing I'm looking for is n choose v of H. So actually, if you go back to the definition, so it's not the case that bigger sets would contain or would count as a copy, because I'm saying that the set has to be of size exactly v of h. So yeah, I mean, in this case, if we're looking at the complete graph, all the subsets have a I mean, every set of size, number of vertices of h counts as exactly one copy in this kind of, yeah, not the most interesting definition, but anyway. So this is, so in the way we're defining it, the complete graph has n choose v of h copies of h. If you wanted the copies to be disjoint, then the most you could do is n over v of h. So maybe that's where this number is coming from. Right. So we're just counting all the copies, and yeah, I can, so yeah, this n choose v of h is the right thing. Okay. So, okay. Yeah. If we were counting kn's in h, then I have no idea. It will depend on h in some crazy way. Well, yeah. Okay. So it's just, yeah, sets of vertices that contain a copy of h are a copy of h. I have to get this terminology straight, but oh well. So yeah, so the way I want to kind of, I mean, I don't know if this is much of an experiment, but so the statement of the theorem I want to prove today is kind of a pain. I'd rather just kind of tell you the proof, and then maybe by the end we'll tell you the statement. So let's basically start by, take a graph and see how many copies of h we can find, and then I'll tell you what the theorem is that we've proved. Let's see how this works. So these are the assumptions I'm going to make. So h is a graph with at least one edge, which is something that has kind of come up on the assignment and stuff. For example, people thinking about this. So like extremal numbers only make sense when the graph has at least one edge. So let h be a graph with at least one edge. Let epsilon be some positive number. So think of epsilon as like 0.0001 or something. And in all of these things, I have to let n be very large, okay? Because, yeah, we're going to have some kind of limit arguments. So, yeah, think of n being very large. So it's large with respect to h and epsilon. And we'll kind of think about how large it needs to be a little bit later. So it could be either. Well, in some sense, I'm saying let n be large with respect to h as a graph, and it could be any aspect of h in some sense. So yeah, for each epsilon and h, I have a sort of function, let's say n naught of h and epsilon, which we're going to sort of work out what that should be later. And then we're letting n be at least this function of h and epsilon. So yeah, it could be, but you could also just take a function of the number of edges and vertices. That would also work. But yeah, so it's kind of any aspect of h, whatever you need, basically. We'll see how this n naught comes up later. Okay. And so this is what I'm assuming, yeah, n is large. I'm going to take G to be a graph with n vertices. And I assume that the number of edges is bigger than the extremal number. And I'm going to assume it's significantly bigger in a sense. Well, it depends what you mean by significant, but where the amount bigger is like kind of epsilon n choose 2. Well, yeah, sort of. So I'm going to assume that G has this many edges where so remember, this is pi of h. This is the limit of the extremal number divided by n choose 2. So in other words, we have pi of h plus epsilon times n choose 2 edges. So remember, pi of h comes from, so pi of h is a natural thing to put here because it's like in the limit, that's basically in the limit, the extremal number, or maybe I'll write it like this. But kind of another way to write this is that the extremal number, is approximately pi of h n choose 2. And so to say that the number of edges is bigger than the extremal number is to say that there's a little kind of epsilon here that we have extra. Is that clear? So this is the setup. This is the assumptions. And my conclusion is I want to find a lot of copies of h in G. Where lots... Yeah. Oh, yeah. Go ahead. Sorry. Yeah. I guess there's some implicit assumption here. Yeah. That epsilon isn't so big that this graph can't exist. Yeah. So we can always assume that epsilon is less than 1 over chi h minus 1. Otherwise, as you point out, I mean, in some sense, we could omit that assumption, but then our theorem is true just because no such graph G exists. And so you can prove anything about something that doesn't exist. But anyway, but yeah, this only makes sense when epsilon is in this range, because that's the only case where this graph can actually exist. That's a good point. Okay, and so I want to find a lot of copies of H and G, where this lots kind of is a function of H and kind of possibly this epsilon and stuff like that. Okay, so this is the setup. G has n vertices, and it has more than the extremal number of edges, where the more is kind of quantified by this epsilon, and n is very large. Well, I get to choose n large. Okay, here's the thing to think about. Imagine I pick 1,000 vertices from G completely at random. Like, how many edges do you expect S to have on average? So often we've been thinking about taking a graph where you generate the edges randomly, and I'm often asking you how many edges are there in that graph on average and stuff like that. But here I'm taking a set of 1,000 vertices. I don't know what G is, but kind of how many edges do you think S should have on average? Okay, so there is a kind of, at least one. Yeah, I would probably agree with at least one. I'm not sure if what I'm going to write is equivalent to what's in the chat. I'm having a hard time parsing it a little bit, but the answer is going to be like what you should expect to see on average is, well, you should expect to see. So, okay, suppose I'm saying that the number of edges is equal to this. I mean, basically any possible edge of S, any possible pair, the chance that it lands on an adjacent pair of vertices is like, the probability of that is basically pi of H plus epsilon. So, I would expect if I chose 1,000 vertices that the proportion of them which are adjacent would be the same as in the kind of ambient graph, like the large graph we're in, right? So basically every pair of vertices should have the same chance of being adjacent as they do in the original graph. So I would expect to see now this kind of random variable, the number of edges in a set of 1,000 vertices. It might be a very nasty random variable, but kind of on average, I would expect to see that many edges if I chose 1,000 vertices. Okay, so that's what I just said. So if an average set of vertices has the same edge density as the global graph, then if you think about it, if I chose, say, 1,000 vertices again, it'd be pretty unusual for that set of 1,000 vertices to have less than, this number of edges, where here the thing to notice is that, so it's the same as what I wrote for the expected value, except that I've got an epsilon over 2, right? It's like, yeah, if you expect this many edges on average, like having less than this number, I mean, it's not unheard of. There probably are some sets that have that few edges, that few number of edges, but it's kind of an unusual situation. So basically, I guess what I'm trying to say is that you would expect kind of a large proportion of your sets of size 1,000 to have this many edges or more, where I've got an epsilon over 2 here, because the average has that many with an epsilon. So you'd expect kind of most of them to have more than this number of edges. So I want to sort of try to quantify this. We're not going to be able to prove that most of the sets have lots of edges, but we'll be able to prove that quite a reasonable number have a lot of edges. Okay, and that's going to be kind of important. But we're not going to deal with the number 1,000 here. We're going to deal with another quantity. Okay. Well, okay. I guess so. What I intended here. So, well, maybe I'll skip this. So, right. So remember that pi of h is the limit of the extremal number over n choose 2. And then so the number of edges. So actually, if I can choose n not big enough. So by the definition of what a limit is, for every epsilon, or here I'm going to use epsilon over 2. Well, okay, maybe there exists an n naught such that this thing here, ex extremal number of h over n naught, n choose 2, is at most pi of h plus epsilon for all n at least n naught, epsilon over 2. Right, that's just by the definition of limit. And then if I multiply by n choose 2, I get this. So there's some n naught such that the So in particular, if I look at n naught by itself, so extremal number for, on n naught vertices of h is less than pi of h plus epsilon over 2, n naught choose 2. So what's the significance of this? So the point here is, so now imagine I go back to my graph h, or sorry, my graph g, which has n vertices. If I can find n naught vertices, like a set of n naught vertices, where there's a lot of edges in here, so there's at least pi of h, or when I say a lot, actually what I really mean is that there's not too small of a number of edges here. So if I can find at least that many edges, then I know there's a copy of h living inside of here. So there, because of this inequality. Okay. So to find a lot of copies of h, it's going to be useful to find a lot of sets of size n naught that have a lot of edges. Is that clear? And this is really just using the definition of pi h. Like, in fact, we're not really applying the Erdős theorem here in some sense. We're just using the definition of pi h. Okay. Yeah, so this is what I just said. If I have a set which has exactly n naught vertices, which has at least this many edges, then it automatically contains a copy of h. And we can kind of use that information to find a lot of copies of h. That's all we're going to really do. But we have to be careful how many copies we're finding and try to make the bounds as good as possible. Okay, so yeah, like I said, so, oh, sorry, this should be epsilon over 2. Oops, epsilon over epsilon. Yeah, so I want to find a lot of sets with n naught vertices which have, a fairly large number of edges. So let me define script D to be the collection of all such sets. So all the sets of size n naught which have a large number of edges, where large is at least pi of h plus epsilon over 2, n naught choose 2. So D here stands for dense. So these are my dense sets, where dense just means it has a lot of edges. Okay, so what I want to show is that D is large. Because if I can show D is large, that's going to help me find a lot of copies of H, because all of these sets in D have at least one copy of H. So let's do this by some double counting. Okay, so first, I guess what I want to know is what should I write here? So I'm adding up over all the sets of size n naught, and then I count the edges inside of S. And I want to say that this counts every edge of G a certain number of times. So can anyone see what I should write here? So how many times does every edge get counted? So here I'm not just summing over the dense sets, I'm summing over all subsets of size n naught. It's pretty close. It's pretty close. So if I take you're missing some -2s. If I take an edge, then, in order for it to be counted, it has to be contained in the set. And then I need to choose, a set of size n naught. But basically, if the number of ways to choose those two is I have to choose n naught minus 2 from n minus 2, or v of g minus 2. So yeah, I think that was right, except for the 2's. Right, so every edge will get counted this number of times. Okay. Okay, well now we're doing some double counting, and we're going to use this D thing. So let's upper bound this thing in a way that involves this set D. So if I sum up over all the sets S, I can split that up in terms of sets which are in D. So this kind of first term I'm counting here is when S is in D, and this is where like S is not in D. When I have a set that's not in D, I know that it's sparse, meaning that it has fewer than this number of edges, right? Because that's how I define D. So here I get to write that this is less than, so I can even write a strict inequality, but it won't matter. This is less than, it has fewer than this number of edges. So, and then I'm multiplying by the number of sets which are sparse. So when I say that a set is, if I say that S is not in D, then I can say that S is sparse. That's the terminology I'm using. And if I say S is in D, I'm saying S is dense, meaning it has a lot of edges. For the dense sets, I can't say very much because, I don't know. I mean, in theory, if I take a set with more than this number of edges, it could have all the edges. I can't really control that. So I'm just going to write n naught choose 2. Because, it could, in theory, have all of the possible edges. Okay, so Right, so this is the inequality we've come to by double counting. So now I want to just kind of rearrange this to get a bound on D, I believe, because that's what we care about, right? We want to show there's a lot of dense sets. So this is the inequality we've just derived. And like I said, all I'm doing here is solving for D, the size of D. So, okay, where do I have a D? I've got one here and one here, which is annoyingly inside of all this junk. But, if you do the algebra, you see that it's, if I just keep the D stuff, it's D times, well, basically everything is times n naught choose 2. I have 1 from this. I have minus that stuff. I move all the other junk to the other side, which looks like this. Okay. And now I want to say, so what can I say here? So, okay, so the way I want you to think, by the way, of this n naught. So remember the n naught was chosen large enough so that the extremal number is what it was, what we said. You should think of n naught as a constant that depends on h and epsilon, right? Because it was. It's like, you can think of it as being the smallest n such that you have this, like the extremal number n naught h is less than whatever, pi of h plus epsilon over 2 n naught, choose 2, right? So it's chosen, it's just a function of h and epsilon. And this kind of addresses, so going back to this question before, does this n naught depend on the number of vertices of h or the number of edges? It's more complicated than that because it depends on the growth rate of the extremal number in some sense. It depends on, it depends on basically how fast this limit converges. Okay, how fast extremal number over n choose 2 converges to pi of h. So it's a bit more complicated than depending on number of vertices or edges. So yeah, n naught is just a constant, okay? So now if we think of n going to infinity, I want to be able to say that I want to get a lower bound on D as some sort of n to some exponent, basically. I hope it's at least 2. It's going to be bigger than that, though, I hope. So how can I kind of quickly think of this? So, I mean, all of this stuff is just a constant, right? It's a positive constant. Actually, that comment about epsilon here maybe comes into play. So I want these two things better sum up to less than 1. But as long as epsilon is small, then it will, because I don't want a negative number. But this is a positive constant. We like positive constants because they don't change the inequality, right, if I divide. This thing's a constant. And then we have to be careful. But so I've got 2 terms here. One is subtracted. So we have to be a little bit careful here because what I want here, I want to say that this is at least like n to the n naught, okay? Which it sort of looks promising because this thing is like, that thing is sort of like n to the n naught minus 2. If you think of n naught being constant, so there is some factorials and whatever here, but the factorial, like the n naught factorial or n naught minus 2 factorial in the denominator is just a constant because n naught is a constant. So that's sort of like that. This thing is sort of like n squared. This is a constant. And then this stuff is like n to the n naught. So I guess you just have to check that this first term is bigger than the second term, basically. Which it is because actually, let's do some counting, some combinatorics. So how would I compare these two things? If I take n choose n naught and then n naught choose 2, and then I want to compare this to n choose 2, n minus 2 choose n naught minus 2. So which one's bigger, or how do they compare? Possibly. So it's kind of a trick question because neither of them are bigger. They're the same. Yeah, so, well, it's the number of ways to kind of take n whatever people, let's say, pick a committee of size n naught, and pick like 2 co-chairs of the committee. So pick 2 special people inside the committee, right? Or you could take your n people, you could pick the committee, you could pick the chairs first, right? You have n people, you could pick the chairs of the committee, and then you could pick the rest of the committee around the chairs. And like these should be equal, right? Does that make sense? So yeah, picking the committee and then picking the chairs inside the committee is here. Picking the chairs and then picking the rest, the non-chairs of the committee, is here. So these are the same thing. Okay, so all I'm really, when I want to say that the first one here is bigger than the second one, all I'm saying is that pi of h plus epsilon is bigger than pi of h plus epsilon over 2, which it is, because there's an extra epsilon over 2. So actually this whole thing just equals, epsilon over 2. This is a little bit too messed up, this slide, but where can I write this? Nowhere. Okay, this whole thing being, on the right hand side is just equal to epsilon over 2 times n choose n naught times n naught choose 2. So this whole right hand side is just equal to that. So that was kind of nice, I think. Okay, so it's positive, and the order of magnitude here is kind of n, like the main thing here, the only thing involving an n is the n choose n naught, which does have size like n to the n naught times a constant. Yeah. Oh, I see. Yeah, you can also cancel here. Yeah, that might have actually, well, I'm not sure if it makes our lives easier or harder actually to cancel that, but that's also sitting there. Right, so the growth rate of this d is certainly, like if I treat epsilon as a constant, h as a constant, and n naught as a constant depending on epsilon and h, then the growth rate is n to the n naught. But that's, I mean, we still haven't counted copies of h, right? So, okay, what we said before is that every dense set, so every set in D, contains at least one copy of h. That was just because of the definition of n naught and the definition of dense. So if I go through every set in D, I will see one copy of h at least. But some copies of h get counted more than once in this sum. So, okay, so what I'm going to write here is, so if I do add up over all dense sets and I count the number of copies of h and s, it'll be at least one every time. So this summand, each thing in the summand is at least one, or each thing in the sum. So that's why I get this inequality, because I get one for everything in D. And now I want to say, how many times could a copy of h be counted by this sum? Like a maximum, what's the worst possible case? So I've got a copy of h, and this is another just counting thing. And the bound here I'm going to give is nothing too clever. Something like that, but not quite like that, what's written in the chat. So, it possibly could, but I'm going to do something here which is like very kind of sloppy. So all I'm going to say is that, I mean, in theory, every set of size n naught containing h, yeah, something like n choose n naught, but not quite. So that you have to remember, I'm always counting the copy of h. So it's like, how many ways can I extend h to a set of size n naught? And it's n minus the size of the number of vertices of h, choose n naught minus the number of vertices of h. Because in theory, every set of size n naught containing h containing that copy of h could possibly be dense. That's a really sloppy bound, but that's all we're going to need to use. So, and this was counting the total number of copies of h and g. So if I want to get a lower bound on this, I just divide by this factor here. So therefore, the number of copies of h and g is at least this thing. So it's the size of the number of dense sets divided by this thingy from the previous slide, which if you think of all of these things being fixed except for n, and think of n growing, right? My numerator grows like n to the n naught. The denominator grows like n to the n minus v of h, because this minus v of h doesn't really make a difference, right? So this basically cancels and gives me an n to the v of h. Okay, which, right, so if I have more than the extremal number of edges by some epsilon n choose 2, if n is very large, then the number of copies of h is going to grow like n to the v of h, at least. But it's also at most, because if you think about it, like this is a constant proportion of the number of copies of h in the whole complete graph. Right, so okay, so on the next slide I'll kind of explain what the theorem was, but Yeah, so what we've proven is that if you have pi of h plus epsilon and choose two edges, right, where n is large, then number of copies is, at least some constant depending on epsilon and h times n to the v of h. But that's like a positive proportion of all the possible copies, right? Because we said even in kn only has n choose v of h copies of h, which also grows like n to the v of h, right, with a different constant factor. So the message here is that if you're beyond the extremal number, then the number of copies of h you have is actually like a positive proportion of the number you would have if you had all the edges. Like it's like some positive percentage of all of the copies. Or in other words, it's like theta of the number of copies in Kn. So this is why I didn't state the theorem from the beginning, because I thought it might scare everybody away. So here's like very formally what we proved. So this is the theorem of Erdős and Simonovits from the 70s, I believe. So for every graph h with at least one edge and every epsilon, we prove that there's a constant c that depends on h and epsilon, and there's some n naught, so some number of vertices n naught that depends on epsilon and h. For whatever reason, I swapped these and these two. I mean, there's no reason to swap them. So don't read into this too much. The fact that this h got switched with epsilon, it doesn't matter. So that if the number of vertices in our graph is at least n naught epsilon h, then every graph with at least n vertices and at least this many edges contains at least that many copies of h. Or in other words, it contains a positive proportion of all copies, where the proportion depends on epsilon. Oh yeah, go ahead. Yep, you could think of it like that. Yeah. So in other words, you could think of it in any kind of way. You could also think of it as a positive proportion of the number of homomorphisms of h into the complete graph on n vertices, or all of these different things. It's all equivalent. Basically, if you're counting copies of h in a complete graph, you get something like n to the v of h with possibly different constants.